Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young. Chapter 2, Projection Section Perspectivity, Elementary Configurations. Section 19, The Fundamental Theorem on Quadrangle Sets. Theorem 3. If two complete quadrangles, P1, P2, P3, P4, and P1', P2', P3', and P4' correspond, P1 to P1', P2 to P2', etc., in such a way that 5 of the pairs of homologous sides intersect in points of a line L, then the 6th pair of homologous sides will intersect in a point of L by assumptions A and E. This theorem holds whether the quadrangles are in the same or different planes. Proof. Suppose first that none of the vertices or sides of one of the quadrangles coincide with any vertex or side of the other. Let P1, P2, P1, P3, P1, P4, P2, P3, P2, P4 be the 5 sides, which, by hypothesis, meet their homologous sides P1', P2', P1', P3', P1', P4', P2', P3', P2', P4' in points of L. Figure 19. We must show that P3, P4, and P3', P4' meet in a point of L. The triangles P1, P2, P3, and P1', P2', P3' are, by hypothesis, perspective from L. So also the triangles P1, P2, P4, and P1', P2', P4'. Each pair is therefore, by theorem 1', perspective from a point, and this point is in each case the intersection O of the lines P1, P1', and P2, P2'. Hence the triangles P2, P3, P4, and P2', P3', P4' are perspective from O, and their pairs of homologous sides intersect in points of a line, which is evidently L, since it contains 2 points of L. But P3, P4, and P3' and P4' are 2 homologous sides of these last 2 triangles. Hence they intersect in a point of the line L. If a vertex or side of one quadrangle coincides with a vertex or side of the other, the proof is made by considering a third quadrangle, whose vertices and sides are distinct from those of both of the others, and which has 5 of its sides passing through the 5 given points of intersection of homologous sides of the 2 given quadrangles. By the argument above, its 6th side will meet the 6th side, respectively, of each of the 2 given quadrangles in the same point of L. This completes the proof of the theorem. Note 1. It should be noted that the theorem is still valid if the line L contains one or more of the diagonal points of the quadrangles. The case in which L contains 2 diagonal points is of particular importance and will be discussed in Chapter 4, Section 31. Note 2. It is important to note how far the quadrangle P1', P2', P3', P4' is determined when the quadrangle P1, P2, P3, P4, and the line L are given. It may be readily verified that in such a case it is possible to choose any point P1' to correspond to any one of the vertices P1, P2, P3, P4, say P1, and that if M is any line of the plane L P1', not passing through P1', which meets one of the sides, say A, of P1, P2, P3, P4, not passing through P1 in a point of L, then M may be chosen as the side homologous to A, but then the remainder of the figure is uniquely determined. Theorem 3'. If 2 complete quadrilaterals, A1, A2, A3, A4, and A1', A2', A3', A4' correspond A1 to A1', A2 to A2', etc., in such a way that 5 of the lines joining homologous vertices pass through a point P, the line joining the 6th pair of homologous vertices will also pass through P. Assumptions A and E. This is the plane dual of Theorem 3, regarded as a plane theorem. Definition. A set of points in which the sides of a complete quadrangle meet a line L is called a quadrangular set of points. Any 3 sides of a quadrangle either form a triangle or meet in a vertex. In the former case, they are said to form a triangle triple. In the latter, a point triple of lines. In the quadrangular set of points on a line L, any 3 points in which the lines of a triangle triple meet L is called a triangle triple of points in the set. 3 points in which the lines of a point triple meet L are called a point triple of points. A quadrangular set of points will be denoted by Q parentheses ABC, comma, DEF, close paren, where ABC is a point triple and DEF is a triangle triple, and where A and D, B and E, C and F are, respectively, the intersections with the line of the set of the pairs of opposite sides of the quadrangle. The notion of a quadrangular set is of great importance in much that follows. It should be noted again in this connection that one or two of the pairs AD or BE or CF may consist of coincident points. This occurs when the line of the set passes through one or two of the diagonal points. We have just seen in Theorem 3 that if we have a quadrangular set of points obtained from a given quadrangle, there exist other quadrangles that give rise to the same quadrangular set. In the quadrangles mentioned in Theorem 3, there correspond to every triangle triple of one a triangle triple of the other. Definition: when two quadrangles giving rise to the same quadrangular set are so related with reference to the set that to a triangle triple of one correspond a triangle triple of the other, the quadrangles are said to be similarly placed. Figure 20. If a point triple of one corresponds to a triangle triple of the other, they are said to be oppositely placed. Figure 21. It will be shown later in Chapter 4 that the quadrangles oppositely placed with respect to a quadrangular set are indeed possible. With notation for quadrangular sets defined above, the last theorem leads to the following. Corollary: if all but one of the points of a quadrangular set Q of ABC and DEF are given, the remaining one is uniquely determined. Assumptions A and E. For two quadrangles giving rise to the same quadrangular set with the same notation must be similarly placed and must hence be in correspondence as described in the theorem. The quadrangular set, which is in the section by a one space of a complete 4-point in a 2-space, the Desargues configuration, which is the section of a 2-space of a complete 5-point in a 3-space, the configuration of two perspective tetrahedra, which may be considered as the section by a 3-space of a complete 6-point in a 4-space, are all special cases of the section by an n-space of a complete n plus 3-point in an n plus 1 space. The theorems which we have developed for the three cases here considered are not wholly parallel. The reader will find it an entertaining and far from trivial exercise to develop the analogy in full. Exercises. 1. A necessary and sufficient condition that three lines containing the vertices of a triangle shall be concurrent is that their intersection PQR with a line L form with the intersection EFG of corresponding sides of the triangle with L a quadrangular set Q of PQR and EFG. 2. If on a given transversal line, two quadrangles determine the same quadrangular set and are similarly placed, their diagonal triangles are perspective from the center of perspectivity of the two quadrangles. 3. The polars of a point P on a line L with regard to the triangles which meet L in three fixed points pass through a common point P' on L. 4. In a plane pi, let there be given a quadrilateral A1, A2, A3, A4, and a point O not on any of these lines, and let A1, A2, A3, A4 be any tetrahedron whose four faces pass through the lines A1, A2, A3, A4, respectively. The polar planes of O with respect to all such tetrahedra pass through the same line pi. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt with programming and illustration by Jim Renhold, 2019. Thank you for listening.